Hello everyone, I'm Chanwei Liu. Welcome to this pre-workshop tutorial on agent-based model with MATLAB illustration. Let's first think about what a model exactly is before we introduce agent-based model. So according to the founding father of our society, James G. March, a model is a simplified picture of part of the real world. So you will be learning a variety of different model families that help you to, capture the simplified picture of a part of the real world. And today we're going to focus on one particular type of model, agent-based model. So here is a definition of agent-based model. So I highlight some of the key phrases in this definition. Let's start with autonomous agent. So imagine the agent you're referring to here is individuals. So individuals can have different traits, memory for example, and different behavioral rules, isn't it? And then in this agent-based model, you create many of these autonomous agents. They will act and then interact with each other. And many of these interactions are so interesting that they cannot be tracked by mathematics. That means that you can't really solve this outcome in a closed form solution. That's why this computational method can be very useful. So using this simulation approach, then you can still try to capture what is the aggregate outcome after all this interaction among different agents with different trait and behavioral rules, and then what is the impact on the whole environment. When you develop an agent-based model, you're acting like a god, creating an artificial world with many different agents. And each of these agents is following a if-then statement you create for them. So this condition, if we incorporate one of the main theory in our field, behavioral theory of the firm, they can actually model this satisficing process for each of the agent. For example, the condition can be each agent will compare the current performance obtained against their historical aspiration. And if the current performance is higher than the historical aspiration, and this agent is happy or satisfied, then the action one this agent will be taken is, just continue the status quo, right? The previous routine is leading to good enough performances, so that routine will be continued with some probability. Otherwise, if this condition is not met, meaning that the current performance is lower than this historical aspirational level, then this agent is not satisfied. So with some probability, he will take action 2, which is likely to engage in change or take more risk and so on and so forth. So each agent can follow this if-then statement, but of course they also have different traits that they may have a different performance function, or their initial performance or landscape they arrive at is different. Or you can make the condition even more interesting by incorporating this interaction among the agent directly. So incorporating this social comparison process. So there will be a social aspiration, probably based on the average performance of each of the agents in this artificial world in a particular period. Then you can have another set of if-then statement, right? And then you can simulate all these agents. After some period of time, you can have this collective outcome. Then you can examine the association between this collective outcome, how this risk-taking is a function of the performance aspiration gap, right? Be the historical aspiration or social aspiration. So this is one of the many possible illustrations of how do you build an agent-based model from the theories you know. There's one caveat when you develop an artificial world like this. You may be tempted to incorporate as many theoretical constructs that excite you as possible in this model, but actually that can be counterproductive. This quote from Professor George Box illustrates why incorporating too many features in your model is counterproductive. So as you probably guessed, this is the origin of the famous quote, all models are wrong, but some are more useful. So according to Professor Box, a good model is one that is simple but evocative. And actually that's the signature of what a great scientist does with their model. And the mark of mediocrity is try to incorporate too many things, over elaboration and over parameterization, so that the model cannot really generate meaningful prediction to be tested. This may sound very abstract, so let me give you a particular example to illustrate what a simple but evocative model is about. This example is based on a model developed by Professor Thomas Schilling on racial segregation. And here is an illustration about the strong racial segregation in New York. And the typical explanation back then in the 60s and 70s is what led to this huge racial segregation? People believe is because people have very strong racial bias. And Thomas Schilling developed a model to challenge that conventional wisdom. I believe many of you knew this model before, but even you do, probably can spend about 10 minutes, go to this website and explore this website. It is an excellent resource to illustrate what exactly Schilling's model is and what is the unconventional insight it generates. So we will continue after you explore this website. Welcome back. I hope you enjoy this website. Now you know what this agent-based model is about. We can evaluate whether this is a good model according to the criteria in Chapter 3, Levin-March. So according to them, a good model should contain truth, beauty, and justice. So what did Levin-March mean by containing truth? Effectively, it means whether the model can be proved wrong. Can Schilling's model be proved wrong? One of the many possible ways is to examine this association between segregation and racial bias, right? Schilling's model will be proved wrong if the more segregated area are associated stronger racial bias. This is one of the many papers that empirically test Schilling's segregation model. And as you can see from the abstract and also from the main text of this very nice article, Schilling's idea received very strong empirical support. Of course, there's some minor difference or minor deviation, like different function form was observed in the data, but in general, empirical data support Schilling's insight pretty strongly. So we can probably conclude this model contains interesting aspect of the truth as observed in empirical research. Next, whether Schilling's model is beautiful. Now I'm going to introduce you to a tool called NetLogo that can help us to examine this question. So feel free to go to this website. You can just Google NetLogo and install this software on your own computer. And then I'll show you how Schilling's model can be demonstrated using this platform. After you successfully install NetLogo, and you should be able to see this interface. And one of the very desirable features of NetLogo is that there's a very rich model library you can explore. So from art, biology, to social science, and also system dynamics, there's a variety building models that can help you to understand some of the key insight and dynamics has been explored but by a variety of scientists in different areas. And this includes Schilling's segregation model, of course. So if you go to social science, segregation, and you open this model, then you'll be seeing interface like this. And it's very similar to the website you just saw, but here you can examine some of the model parameters more easily. So how do you play around this model? Well, first of all, you set up this artificial world. So this is what you already knew from the website, right? There's a neighborhood, and you have two types of agents here. One is represented by red, and the other represented by green. And they're randomly located on this neighborhood. And they have this behavioral rule. They would like to move when they're unhappy. When they're unhappy is that they're the absolute minority in their perception. In this case is the neighbors around them, they are fewer than 30% of the neighbor are of the similar type. So once you have this behavioral rule set up, you can actually begin to simulate this model. You can go once, for example, that all this unhappy agent will try to move to an empty space. So you can see each of them will move around if they're unhappy, and you can also see this indicator, the percentage of the similar as an aggregate outcome in this world, and how many of the agents remain unhappy. So you can also have this number of agents, similarity, number of happy and unhappy documented over here. And go once for another time, and then if you're not so patient, you can actually go continuously until you reach a stable outcome. As you can see here, now the model stopped because that was written in the code whenever all the agents cannot really move to another space and all of them are happy, and that will lead to this stabilized outcome, right? As you can see, this segregation is visually clear. You have this area dominating by red and dominated by green, respectively. So you can also use this model to examine some of the possible changes or different boundary condition. If you want to do that, you just redo this computational experiment, right? Let's create another artificial world by press this setup. Then you have a different initial condition with then randomly allocated in this different space. But then you can say, well, what if people do have very strong racial bias? Like actually they have a strong racial bias like 90%. They really will be unhappy if their neighborhood contains different people. That's a really strong racial bias, right? So let's go once and see how it turns out. Well, there's some changes, but let's go another round and it's not clear what's going on. So let's go round and round for several times. Well, this is something potentially surprising, right? In this sense that people just keep moving around. And the reason probably is clear in hindsight is that when people have very strong racial bias in terms of this very high similarity they're pursuing, then they will continue being unhappy. And when they're being unhappy, they will continue moving around, and actually segregation, the stabilized segregation, is very unlikely to be obtained. So the real world observation that you have this strong segregation can only be obtained when people have a much weaker racial bias. So as you can see here, if we change this this parameter to about 70% or 69%, as you can see, well, very strong segregation emerged, right? So later on, actually, some literature linked this to the tipping point. So some of the threshold mechanism can occur once this parameter kind of change even slightly, but the collective dynamic can be very dramatically different. And we just saw one of the possibility, right? But you can see this high value of this parameter will lead to this random changes still among some of the unhappy agent here. So if you continue change that and lower than 60, and then they all settle. They're reasonably happy and no one wants to change anymore. So this can be something you can explore during your free time. But how do you change all this parameter so that you can find some of the surprising like tipping point or other boundary condition of this very simple model? And another very desirable feature of NetLogo is that for all this classic model they incorporate in this model family, they have a very clear briefing about what this is model and how do you use it and things you can explore and play around with. And also they incorporate this code that you can modify to some extent to test your boundary condition. Because the interface here, there's only one variable you can really play around. Here you can also play around the initial density. Let me just show you quickly that if you have this setup, creating another world, you can have a much lower density. It basically means that there's more empty space. And of course, sometimes this kind of dynamic can change dramatically based on this initial condition. And if you want to be more complicated and incorporate other feature, obviously you can modify the code and change the interface. Then presumably you can incorporate those features that interest you, and you can investigate the impact of those features as well. Using NetLogo, we explore this question about whether Schilling's model is beautiful. I think there's some evidence to suggest this is a pretty beautiful model, isn't it? That is very simple, and the threshold mechanism in particular have been applied in all the type of model, like adoption behavior. You're more likely to adopt a technology if many of your neighbors or many of your friends have adopted something. And that is very similar to the dynamic developed in Schilling's model. And finally, it is a beautiful model because it provides some surprising insight that people did not expect. And as we saw from the NetLogo illustration, that people believe that strong segregation resulting from strong racial bias cannot really hold. When you have very strong racial bias, actually this segregation is unlikely to be observed. So this is a pretty beautiful model according to Liv and Mark, their criteria. Next, is Schilling's segregation model a good model in terms of the third criterion? Does that contain justice? I think one of the illustration on the website suggests yes. It kind of provide normative implication that can help us to make the world better, right? So in that illustration, they suggest people are unhappy with the absolute minority, but if people can learn to be unhappy and move around when they're the absolute majority, then actually it will lead to a much more desirable collective outcome with very low segregation and very high diversity. So Schilling's segregation model is very simple, but allow this type of very useful normative implication that can direct us to make the world better. Here is an important caveat. NetLogo looks great for teaching and illustration purpose, as we saw. But for research purpose, if you want to publish in top journals, then many of these reviewers will look for robustness check in your simulation result and so on and so forth. And NetLogo is not so useful for that purpose. For that purpose, you need tools like MATLAB or Python or Julia. So these are all the tools that the faculty who will be teaching this summer school have been using. And then I will illustrate some of the ideas about how do you use MATLAB for building this agent-based model. Then obviously for you, it's really a choice for yourself that evaluate what is the purpose for you to do modeling, and then select the suitable tool for your purpose and accumulate the experience so that you know all this modeling trick and useful shortcut for applying that tool. And for each of the tools I talk about here, Python, MATLAB, and Julia, there are some free courses online like those in Coursera you can explore. So here, the tutorial will really focus on the aspect about how do you build the agent-based model using MATLAB. And some of the very basic operation, how do you make the MATLAB to work, I will refer you to some of these courses online. If you have time, feel free to explore them before you coming to the summer school. That will really maximize your learning outcome. This illustration is based on Model 1 in this paper, co-authored with Jurgen Daniel, also a faculty of this summer school. Before I use MATLAB to illustrate how do you replicate this model, let me elaborate what is the motivation of this model. One of the motivation is, well, exceptional successes attract our attention, right? In the business school, we focus very much on this top performing firm, the richest people, or if you talk to people outside the business school, probably people pay a lot of attention to this very high status, highly paid sportsman, right? But then one of the question is, of course, exceptional successes, do we attribute these successes to their skill or luck? By skill, we mean the dispositional factors of the individual or the firm, like their skill, effort, or grit, persistence. Or on the other hand, can their successes be just a matter of luck, like being at the right place at the right time, all these uncontrollable situational factors? If a success should be attributed more to skill, then presumably learning from this success is more constructive and useful, right? But if a success should be attributed more to being at the right place at the right time, then learning or replicating this routine from these successful firms can be detrimental. So that's the idea. To examine this question, of course, we need to be more precise, not just saying that successful firm or individual are luckier. So let's try to develop a model to quantify this impact of luck. So this model is based on the context like this. Consider there's a game, a lot of players are playing this game, and there will be an outcome after several rounds of this engagement. So the intuition suggests that if you observe a player that continuing winning this game, it's unlikely to occur by chance, right? This actor or this agent must very likely to have higher skill so that he or she can continue winning this game. Let's examine when that intuition is correct. Let's first assume all these players who play this game have a level of skill, drawing from a distribution like this. So the probability of success or winning in the first period is equal to this CI. So for each player I, he has the value of the C representing the capability or skill, drawing from this distribution. So as you can see, this distribution has the bell shape. So it means that the majority have a moderate skill. So 50% of the time they'll win, 50% of the time they'll lose. But there's a minority have very high skill and a minority have very low skill. So a normal shape distribution, nothing really strange about that. But we want to make this model slightly more realistic. We want to model this so-called success, pre-success dynamics or performance dependency. If you succeed in the past, you're more likely to succeed in the future. Or you can say a rich get richer dynamics. How do we model this? One way to model this is this. So assuming you have a player, I, then the initial capability or skill starting from here, but then the probability to win in the next round depends on what happened in the last round. In the sense that if this player happened to win in the last round, then you will get a boost for the probability to win in the next round. So in this way, so it's regulated by this parameter W. So each player I have the C representing the skill and also this W representing the strengths of this success, pre-success dynamics. But don't forget, success pre-success dynamics can be a double-edged sword. What if this player failed in the last round? Well, in this case, it will get a penalty, also regulated by the same parameter W. That's it. That's the only two parameter we assume in this model. So each player have a value of C representing the skill of this agent, drawing from this bell-shaped distribution. And each player also have this W parameter that representing the strengths of this success, pre-success dynamics. and the value drawn from this uniform distribution. So what do we want to learn from this model? Well, let's assume there's a lot of players playing this game, say 1 million, 10 million, doesn't matter, and each of the players playing this game for 50 times. So the lowest performance possible is really 0, right? Obtaining number of success equal to 0. That's the minimum performance in this case. And the highest performance is 50, like winning 50 rounds in a row. That is an exceptional success in this model. So for each player simulated, this player will have an initial skill, the CI, and then of course the probability of winning will change as a result of their prior outcomes, right? And then for each of the players, they'll obtain this eventual number of successes in this 51 intervals, right? And then we try to compute what is the average skill for each of the 51 interval, and of course for the actor that fall into that particular interval. What should we expect of the association between this average skill and number of successes? Well, our intuition suggests probably there's a positive association between the two, right? Higher performance or higher number of successes are associated with higher average skill. Here's the result. The intuition that higher performance indicate higher skill is true, but up to a certain point. So after you see this number of successes greater than 42 or 43, the threshold, then average skill actually is decreasing with the number of successes. And in particular, the highest performer, they do not have the highest expected skill. Instead, the second best performer in this case is those actors who obtained about 40 to 44 successes. Actually, they have the highest expected skill. So that is what we mean by, well, the second best. Those actors around the non-monotonic kink. And this non-monotonic pattern is also symmetrical in the low performance range. That the worst performer are not the least skilled one, and then the second worst actually is the least skilled one. So how could we obtain this result? Non-monotonic pattern and deviate from people's intuition that higher performance are better. So let me represent the result in a different way to elaborate what is the insight from this model. So let's assume we know two types of players. One type, they're from the context where this W success dynamic is very strong, 0.9. And the other type of player, they're from a context where this W is very weak, success dynamic, very weak. Two observations can be drawn by comparing the scatter plot between this actor from these two contexts. The first observation is, well, the correlation between success and skill is much lower when W is very high compared to when WI is very low. So here, the scatter plot between success and skill is kind of all over the place, right? And then take a look at this particular player. What is the number of successes obtained? Wow, exceptional, right? Winning 50 rounds in a row. But what is the skill level of this actor? Well, just mediocre, right? Or below average. So how could this actor obtaining 50 successes in a row? Now you realize probably to illustrate the enduring impact of early luck, right? So even the initial skill is not great, below average, but this actor can get lucky initially. And then when he succeeds in the first round, what happens to the probability to succeed in the second round? Well, will be boosted substantially because of this high value of W, right? So he's more likely to succeed in the second round. And then what happened for the probability of winning in the third round? Well, will continue being high. And this actor can continue being lucky 50 rounds in a row. So that is an illustration of how early good luck can have enduring impact on the eventual performances obtained, right? And also take a look at this actor. This is an illustration of bad luck, right? The skill of this actor actually is pretty high, above average for sure, but the outcome he obtained is really the lowest possible, 0 successes. So this is just like a mirror image of what happened, right? It must be he or she is most likely to lose in the first round, and this initial bad luck can have, again, enduring impact, almost like creating this trap, very difficult to come out with, so that this actor continue losing and having 0 successes in the end. In contrast, the high correlation coefficient between these two variables when W is very low suggests that, well, in this context, you do need to have very high skill to obtain a lot of successes. So that's why the correlation coefficient between the two is very high. So that is the first observation. The second observation from comparing these two scatter plots is even more important. So in the sense that, well, if you observe this exceptional performance, it's much more likely to come from the context where this W is very high, right? There's a very rare, almost none of the observation can be obtained for this greater than 40 successes when you have a very low W. So this suggests that, well, if you observe an exceptional performance in this model, that is, a success is greater than 40, which context they're more likely to come from? Well, where this W is very high, isn't it? But when W is very high, you are not sure whether those exceptional successes indicate high skill or early good luck. And that is exactly the reason why you observe this expected skill going down after this 42 or 43 successes. Because after that threshold, actually the unreliability of performance increased dramatically, then early good luck can overwhelm the skill, and that is essential to obtain exceptional successes in this model. So you probably observe I insert this photo of Bill Gates here. Actually, it's based on an article I wrote for BBC. Because this suggests an interesting implication drawn for this observation of the model, right? In the sense that you may want to copy the most successful when you look for the potential benchmarking, right? But this model suggests that can be really detrimental. Even you can replicate everything Bill Gates did as an exceptional performer, but you may not be able to replicate his initial fortune, which is essential for achieving exceptional success like this, right? And why we use Bill Gates' example? Well, 2 reasons. On one hand, we know this is a context where this success breeds success dynamics, or economists call it network externality, is really essential in this context about software adoption. So he's really in this context with very high W. That means it's not clear whether he does have high skill or it's just being lucky early on. On the other hand, if you read his autobiography, he actually openly admits that the role of luck in his early success. For example, he was born in a rich family and they happened to live next to a school with the computer lab. Basically, he said he cannot really imagine there are more than 50 kids at his age will have access to computer like he did. Of course, we have to give some credit to Bill Gates that he chose to spend most of his time when he was a kid in computer room instead of playing outside. But still, that access to opportunity suggests that he's really fortunate. And you can also imagine someone with the equivalent, if not superior, potential and skill in programming, but not as lucky as Bill Gates. They may never have a chance to realize their potential, right? And that is another reason why the most exceptional performer, probably we should not expect their expected skill or initial skill or potential to be the highest. So rewarding them or replicating their routine and so on and so forth can be detrimental in this sense. So now I have elaborated the motivation of this model and some of the interesting implication drawn from this model. And now we can use MATLAB to implement this, well, in many ways, toy model. So this model can be implemented in a variety of different platforms, and this is just one of the possible illustrations using MATLAB. So I include this file .m, that is the file for MATLAB. So I upload it if you want to play around later yourself. So these are the codes, and with this percent sign, this is the illustration or the explanation for each line of the code. So the model and the result I just showed you, they can be implemented within 52 lines of the code. So let's start by running this code. So when you press this run, basically run the entire file, all the codes that in this .m file. So as you can see, just within 0.23 seconds and produce a result like this. The association between average skill and the number of successes. And let's duck this figure so that we can see how this result change over time. And this is based on just 10,000 simulated players. And you can see all these variables you created and simulated are listed here. But let's start from the beginning so you can see this step-by-step changes. So we can actually use clear and press enter. Then you clear all these results here. And we can start from the first part of the model or the code. So the second line is clear previous result, and TIC and also TLC at the end is really try to estimate the running time for the codes that between these two lines of command. And then you first initiate this variable, which is the number of simulation. We can say 10,000 to start with. As you can see, it takes just 0.23 seconds, right? And then later on will increase to 1 million. As you can see, for computational method, it doesn't really matter as long as you write your code in an efficient way. And then, like I assume in the model, we allow each player to play this game for 50 times, right? So you can say this is a number of period or number of rounds of this game. And then each player will have a skill represented by this C, and also the pre-success dynamics for the context this actor happens to be in. So the parameter C and the parameter W. In this case, we randomly draw from a distribution. In this case, it's a beta distribution. So in case you have doubt, you can always use the search command here and search what exactly this command is for, and you double click. So this command is help you to draw a random number from this distribution. In this case, it's the beta distribution. For beta distribution, you can use Wikipedia or whatever to learn the basic property of this random, beta distribution. And in nutshell, is regulated by these two parameters, A and B, and determine its shape. And the value drawn from this distribution, of course, is always between 0 and 1. So this is a pretty good representation of a probability of a parameter that represents probability, which is the case for C and W here. So we assume this C is drawn from the parameter 5 and 5 for this beta distribution. And then this actually represents a bell-shaped distribution as we saw from the slide. And then you also have to tell MATLAB, well, what is the size of this C you want to create? So in this case, this matrix is actually determined by, well, just one row and n column. So each of the column basically represent an individual, and we have 10,000 column in this case representing 10,000 individual being simulated. Similarly, we want to create this W, which is the dependency parameter, right? Also drawn from a beta distribution, but now the parameter become 1, 1. So this is to represent this uniform distribution. So value between 0 and 1, each value is equally likely to be drawn between 0 and 1. And of course, this is representing each individual will have a specific W value representing their specific success, success dynamics in that context. Then the other very important variable is the probability of winning at each period will change. Not just the function of the skill C, but also the function of what happened in the last round. So we want to initiate this variable using a matrix containing all 0 to start with, because it will change over time. So initially you assign 0 to this matrix. And then this matrix have T rows. So each row representing the outcome for one particular period. And then for each individual, it will have that probability at each period. And then, of course, initial period, the probability of winning is determined purely by skill, C, because there's no prior outcome in this model yet, right? So probability for the first period and for each individual just equate to the first row of this C variable. And then this basically assign the probability of winning for the first period actually just based on each individual their skill. And then we also want to have a variable documenting how many successes each individual obtain after 15 rounds. So in this case, we just need to initiate this matrix to be for the eventual period, how many successes were obtained by each of the individual. And this is interesting in the sense that, well, this is like a random variable created. This is a uniform distribution with the T period and N individual. As we can see here, that actually is comparing to the probability obtaining or regulated in each period. That basically is like a coin tossing process. So you're comparing this probability of winning of this player with this chance variable. And then if the statement, the condition is met, that probability beats chance, basically, then this player obtained a success. Otherwise, you obtain a failure, as this suggests. But before we go there, let's try to run the first part of the code first to initiate all this initial condition. So instead of run the entire code, you can copy this code and sorry. So I must have did something strange, and so you can always clear command window, and of course nothing will, no harm is done. So and you copy this part of the code and you paste over here, and then you press run, and then you can see here this variable in this line are initiated here. Let's take a look to see whether it's doing what you asked MATLAB to do. So let's start with the first two variables, N and T. There's just one value, which is exactly what you want here, right? And then the variable of C, you can double click on that, and then now you can see this value of C for each of the 10,000 individual. Each of them will have a different value drawn from this beta distribution with parameter 5, 5, right? And then also for W, again, this is also a beta distribution, but it's drawn from this uniform distribution. So each of the individual have the C and W. That's great. And then let's take a look at this probability. So probability, this variable, now we only have value for the first period, t equal to 1, right? The rest is all 0, as you design here. So it was a 0 matrix, and only the first row equate to the C of this individual. Right, take a look at the three first value. That's equivalent or equal to the this value from C, right? That's exactly what you asked MATLAB to do for you. And then you also have the success and chance, and you can take a look at chance. This is variable, so it's all kind of uniformly distributed, and you have this value for each period for each individual. So now you know this model is set up rightly. You need to write these loops to determine what is the number of successes obtained in each round, and then how that change or update this probability of winning in the next round. So the loop works like this. You first, for each individual, from 1 to n, and you have to assign this j as a parameter so that it will loop in each of this for and and loop. So for each individual, and for each period from 1 to t, then we have this if-then statement in this agent-based model, right? So if the probability for this a j actor in this I period, so let's start from 1 and 1. For the first actor and during the first period, if that value is greater than this randomly drawn variable from chance variable, then it basically suggests this actor, the probability of winning, beat chance, and then he obtained a success. Then, in this case, you should update the number of successes. So for this variable success, for this particular individual, then the number of successes plus 1. But this is just one variable you need to update, right? The other very important variable is what happened to the probability for this actor to win in the next round. Well, for this particular actor J, the probability to win in the next round is I plus 1. And it will be regulated from this process. And this is identical to the process I show you in the slides, right? So this probability times 1 minus W, and this W is for this particular individual, and then also plus this W value. But this is just one of the scenario, right? What if this probability value is smaller than this chance value? Then you use this else to describe what happened in that scenario. So in this scenario, basically is otherwise that the success likelihood does not be the probability, so no success in this period. So this line of code actually is optional because without updating, actually the success number will not change either. But just to have the clarity, we have the success for this particular individual remain the same, does not change. And the probability will change, although that the probability for this J player in the next round will be penalized, right? So the current probability will be penalized by multiplying with 1 minus W for this J player. And then you just finish for this particular player, this loop for each period, right? So after 50 rounds, and then this particular player J then will obtain successes. And these successes, of course, is moderated by each of the probability as updated by the previous outcome. And then you also finish the outside loop that you finish this for each of the individual or player in this model. I just complete the process. This is exactly only the 2 loops you need to complete this model. For each player, for each period, then the probability of winning is a function of C and also a function of this prior outcome. And they just keep updating that, and you can obtain this number of successes and so on and so forth. But now to obtain this eventual graph, then you need to try to find a way to compute this average skill for each of the possible number of successes, right? Between 0 and 50. So to compute that, you have to create some additional variable to capture those as well. So let's first say you have this CI sum, and then also have count. So CI sum, basically you first sum all the skill of the individual from each of the interval, right? And count is count how many individual in each of this interval. And then basically you just need to use this CI sum divided by count, then you have the average skill for each of the 51 intervals you will be having, right? And then for this axis from 0 to 50, you can also create this to facilitate the plotting. So now this, again, this another loops, 2 loops here, help you to compute what is the average skill as a function of the number of successes. So here, for I equal to 1 to t plus 1, why do we have 1 to t plus 1? Well, t equal to 50 as we initially defined, right? But here, actually the number of successes, there's one additional possibility, which is 0. You obtain none of the successes out of these 50 periods. That's why when you develop this I or scenarios, 51 intervals, you have to consider that and plus 1. Then for each of this I interval, then you have to find for all this individual whether they fulfill this condition. So here's the condition you design. So if the number of successes for this j individual is equal to I minus 1, so in this case, I minus 1 for the first loop is 0, right? That is the lowest possible performance obtained. So if a j player satisfies this condition, then for this CI sum for this particular interval I equal to 1, then it will sum this the capability of C for this particular individual. And you have to update this number of player in this interval as well. Use this count variable plus 1. Otherwise, if that individual in the first condition is not met, that is, the number of successes obtained by that j player is not equal to this particular I minus 1, then basically these two variables remain the same. No update will happen. And then for each of this interval, then you run for all these individuals. And after you complete all this individual for a particular value of I, then you can move on to the next loop where the I value now move on to 2. So you start from 1 and move on to 2 and so on and so forth until 51. And then you can update this value for your plotting x-axis as well. So for each of the interval, actually you'll have this I minus 1. So as you can see here, the first loop, actually your axis value will be 0, 1, and so on and so forth, all the way to 50. So that's how you develop this x-axis value. Then, like I said, after you successfully implementing this loop, then the expected value of your CI, that is the average skill, is simply taking the this CI sum divided by the count, this variable. And that will be the average skill for each of the 51 intervals you have here, right? Finally, you have all this information now, you can plot it. So when you plot in MATLAB, you just use plot and assign the x variable and then also the y variable. And here are some optional parameters you can use to make this line look better, like this k representing what is the color of the line you want to use, k representing black. If you use b, actually referring to blue. And you can say the line width and the marker is a square and the color of the square is black as well. And you can also have the edge of the color, face color, and the mark size. So you can use this function, of course, plot and the search here, and it will tell you all this possible parameter you can use to make your plot looks better. I'll leave you to explore, and here are just some basic feature you can incorporate. And also try to give a name to the x and y axis, like x label. You can assign number of success and y label average skill to each of them, and change the font size and whether to make it bold or not to make it look nicer. So basically, this is what this code is doing. Then we can run it, right? So when you run it, and we can go back to the command window, then as you can see here, and each time you run it, it will return this estimate time for you as well for running this model. And you can see the result here does not look so nice compared to the result I show you on the slides, right? And that is a very important feature of agent-based model or computational approach. So how do you get a more precise result? Well, the precision, of course, increases with the number of simulation you have here. So let's say we have another 0, and then we press run again. Well, it takes slightly more time, right? Actually, almost like 7 times of the time compared to when you only have 10,000 simulation. Now we have 100,000 simulation. As you can see, the pattern here is much more smooth. So it basically suggests you have better precision here. So if you're not satisfied, feel free to add another 0. And the time here, of course, now it takes even longer. Now we have 3 seconds, but this result is pretty nice looking and very resemble the one we saw from the slide, right? And of course, if you really want to impress the reviewer, you can actually create another 0. Then we have really substantial number of players being simulated. It will take you some time, but that result can be considered really robust, right? all this randomness you introduce in this model, that this probability and the chance comparison, if you don't have sufficient number of simulation, then it can create some fluctuation in your result. But if you have a large enough number of simulation and all this a bias or noise will cancel each other out, and the eventual result you obtain in this graph will look very smooth and very precise at describing the aggregate outcome, the collective outcome based on the model you assume. So I managed to talk for 40 seconds as it's simulated. So now we obtain this very precise result from this model based on a lot of simulated players. So this is a very simple illustration or implementing a toy model from a published paper. And feel free to explore the code I uploaded. You can change the parameter or even change some of the processes here, and feel free to do that and let me know if you find anything surprising. To wrap up, we talk about what a model is and what a good model should contain. And we also talk about different aspects of an agent-based model, right? And in a nutshell, you should try to connect all these micro behavioral rules and motivation of this agent to the macro phenomena in a meaningful way. And we also introduce several different tools you can potentially use for do modeling and of course for your different purposes. And the key is really understand what is your goal of doing modeling and then select a suitable tool for fulfilling your purpose. So thank you for bearing with me for this tutorial, and I hope this is somewhat useful for you, and I look forward to seeing all of you in INSEAD this summer. Thank you.